Introduction to vectors. Now, let's understand how to represent vectors as Cartesian vectors. So, what we normally do is Cartesian vectors are written in a square bracket where we write x component first and then the y component, right? Remember, it is the square brackets which specify that it is a Cartesian vector, right? X value and y value. Few things important to understand here is that when we say x and y values, then we don't say from where you start. So in a grid, you can start from anywhere, but this is change in x value and change in y value, which gives you the vector. And also, that change in x value and y value will give both magnitude and direction. For example, let me take an example and say, let's draw some Cartesian vectors. An example is, let's say 2, 3, right? So vector 2, 3, and let's call this vector as u. So vector u, which is 2, 3. So here we have a grid. So what we can do is that we can start from anywhere. Let's say we start from here, right? 2 means change in x value is 2. So from here we go here, and then 3. 1, 2, 3. So that becomes the vector. And so this vector is 2, 3, right? And we'll call this vector as u. Now, we could have started from some other location also. Let's start from here. And we can go 2 and then 1, 2, 3. There you are. So this vector is also u and it represents the same thing. 2, 3. Do you see that? So we can draw any number of vectors on our grid. All will be equivalent vectors. Exactly the same vectors. Why? Their magnitude is same, their direction is same. Right? So on a grid, we can represent this vector u in so many different places. So place or position is not very important. One position, however, is very critical and it has some special significance. It also helps in doing faster calculations. And that is if you place this right there at the origin. Right? Here. Now, if I do 2, 3, that is 2 and 1, 2, 3, that's it. So it becomes like this, 2, 3. So this one with tail at the origin is called the position vector. So position vector will have tail at the origin. So that is kind of special, but all are same u vectors. Is that okay? So at times, when you are given a vector in this form, you can think that it is a position vector with tail at origin and head at 2, 3. But in case the tail is a different position, for example, if I have a vector AB, right, and vector AB is equals to 2, 3, right, and let us say our tail is at, remember this is not a square bracket, tail is a location 1, 2, let us say, right, then what is the location of head? Can you work that out? So head should be 2, 3 away. So 1 plus 2, which is 3, and 3 plus 2, which is 5. So head will be 3, 5. Therefore we can say vector AB, which could be written in Cartesian form as 2, 3, starts at, has a tail at, or the initial point at 1, 2, and the terminating point or the head of the arrow is at 3, 5. Do you see that? So that's how you can translate this into a vector which is geometrically represented. And if you are given geometric vector, then you can translate it back to the Cartesian form. Do you see how? 3 minus 1 gives you 2 and 5 minus 2 gives you 3. That's how you can do it, right? So I got all these things here for you to remember. Now Cartesian vectors, they are represented with ordered pair inside square bracket. Do you see that? Ordered pair provides the two components which are along x and y axis on the grid. Starting point is not fixed, as you have seen. It could be anywhere. If the tail of the vector is at the origin, then it is called position vector. Do you understand? It's very important to have a position vector. That is it, right? Now the question for you here is, write the following geometric vectors as Cartesian vectors, right? So I have some vectors here without arrows. Now I'm putting some arrows here. So this is the first one, this is the next one, and this is the third one, right? I'll appreciate if you could write for all of them Cartesian vectors, correct? So let me label them. So this is my vector A, this is my vector B, this is my vector C. So you could write A, B, C, or you could always write Q to P, right? N to M or S to T. Any way you like, right? So that is an exercise which you should do, and I hope you don't find any difficulty in this, right? So we can do, and the strategy here is you can either count initial point and see how much x distance you go. So from here we get 1, 2, 3x. So it is minus 3 because going left. So actually I can write vector PQ, which is same as for me vector A. So these are different ways of writing, and that's why I'm saying you. If I am representing them in the geometric form with tail and head, then PQ is good, right? Or rather, I did a mistake. It should be Q to P. Then QP is the correct thing to write, right? And A vector, right? So from Q to P, 1, 2, 3 steps left for the x. So minus 3. And how much down? 1, 2, 3, 4, 5. Minus 5. That represents vector QP. Do you get it? That is how you can get your answer and translate your geometric vectors into Cartesian vectors. I hope you understand and appreciate the concept. Thanks and all the best.